Hello, space enthusiasts. Welcome to another epic journey under the stars, where today we dive into one of the greatest voyages ever undertaken by humanity, Voyager 1. This steel-winged bird, launched in 1977, has become the first human-made object to break free of the sun's bubble and now drifts through true interstellar space. If you're fascinated by tales of human curiosity stretching into the cosmos, please like, subscribe, and share this video. And let's explore together how it all began, what discoveries Voyager 1 has made, and where this bold explorer is heading next. The story starts on September 5, 1977, when NASA's Titan IIIe rocket roared off from Cape Canaveral, carrying not one but two twin probes, Voyager 1, destined for Jupiter and Saturn, and Voyager 2, bound for Uranus and Neptune after its siblings' encounter. Dubbed the Grand Tour, this mission would exploit a rare planetary alignment that occurs only once every 16 years, allowing each probe to slingshot from one giant world to the next without huge fuel reserves or complex propulsion systems. Voyager 1 was the faster of the duo, its trajectory engineered to intercept Jupiter in March 1979 and then swing around Saturn in November 1980, before climbing out of the plane of the planets toward the stars beyond. When Voyager 1 arrived at Jupiter, it came within just 350,000 kilometers of the planet's cloud tops, closer than many of its icy moons' orbit. Its cameras beamed back the most detailed views of the Great Red Spot, a storm larger than Earth itself, along with swirling belts of ammonia clouds in vivid hues of orange, white, and brown. Instruments measured Jupiter's magnetic field as nearly 10 times stronger than Earth's, trapping intense belts of radiation lethal to human crews. Voyager discovered faint rings of dust around Jupiter, previously invisible, and entirely transformed our understanding of its volcanic moon Io, detecting plumes erupting kilometers into space, making Io the most volcanically active body we know. Next came Saturn, whose ring system Voyager 1 probed in unprecedented detail. In November 1980, the spacecraft skimmed through the narrow Cassini division, the gap between the bright A and B rings, and mapped the size, shape, and composition of ring particles, from tiny ice grains to meter-sized boulders. Voyager's spectrometers unveiled the chemistry of Saturn's atmosphere, while its magnetometer charted the shape of Saturn's magnetic bubble. But it was the flyby of Titan, Saturn's largest moon, that stole the headlines. Titan's thick orange haze hinted at a nitrogen-rich atmosphere, the only such moon in our solar system. Though Voyager could not penetrate those clouds, its data paved the way for the Cassini-Huygens mission decades later, which finally landed on Titan's surface. After these encounters, Voyager 1 adjusted its path to leave the ecliptic plane forever, heading toward the outermost reaches of the sun's influence. Yet no one could predict how long its radioisotope thermoelectric generators, RTGs, would provide enough power to keep instruments alive. Those RTGs, fueled by plutonium-238 decay, would slowly lose output each year, forcing engineers to conserve every watt. Even today, more than 40 years later, Voyager 1 still beams back data, powered by less energy than a standard household bulb. The greatest milestone arrived in August 2012, when Voyager 1 crossed the Heliopause, the boundary where the outward pressure of the solar wind gives way to the interstellar medium. For the first time ever, a human-made object entered interstellar space, opening a new window on the particle soup between stars. Voyager's plasma detector recorded a sudden rise in the density of charged particles. Its magnetometer saw the solar magnetic field fade and interstellar fields strengthen, and its cosmic ray instruments mapped a surge in high-energy particles that the sun's bubble once deflected. We were no longer inside our sun's protective bubble but sailing into the galaxy. On board Voyager 1, you'll find 7 main scientific instruments. Plasma spectrometer, to sample the density and temperature of solar and interstellar particles. Cosmic ray detector, to measure the energy and flux of high-speed ions and electrons from deep space. Magnetometer, to chart the intensity and direction of magnetic fields around planets and in interstellar space. Photopolarimeter, to analyze reflected sunlight and study ring and cloud particle properties. Ultraviolet spectrometer, to detect ultraviolet emissions from planetary atmospheres and interstellar gas. Imaging system, a pair of narrow and wide-angle cameras capturing iconic color photographs on magnetic tape. Dust detector, to sense tiny dust grains that pepper spacecraft at high velocity, revealing clues about ring composition and interstellar dust streams. All that technology is controlled by a computer with memory measured in tens of kilobytes, yet it managed to record and transmit millions of bytes of invaluable data. Perhaps the most poetic cargo is the golden record affixed to both Voyagers, a phonograph record engraved with symbolic instructions for playback, carrying greetings in 55 languages, a medley of Earth's music, from Bach to Chuck Berry, natural sounds, thunder, whale song, bird calls, and images depicting life and culture on our planet. It is a message in a bottle cast into the cosmic ocean for any advanced civilization that might one day find it. Communicating with Voyager 1 today is an exercise in cosmic patience. Its high-gain antenna beams data back to Earth with a mere 23 watts, less than a nightlight, across over 22 billion kilometers. Radio signals traveling at light speed take more than 20 hours to reach us, so every control command requires nearly 2 full days round trip. There's no real-time chat, only a steady trickle of scientific reports. As Voyager's power generation gradually declines, engineers have systematically powered down non-essential instruments. First, the ultraviolet spectrometer, then cameras, and others. Each deactivation frees a few more watts for mission-critical detectors. This strategy could extend the craft's scientific life into the 2030s, making Voyager 1 one of the longest-lived robotic explorers ever built. Voyager 1 is not just hardware, it's a cultural icon. Its journey reminds us that a small, precise instrument can outlive entire civilizations, drifting ever onward into the unknown. Every faint signal we capture is a testament to the ingenuity and perseverance of countless engineers, scientists, and dreamers who believed in exploring where no one has gone before. What comes next? Voyager 1 will continue sailing through the Oort cloud, the vast comet reservoir surrounding our solar system for perhaps tens of thousands of years. Its instruments will eventually fall silent, but the spacecraft itself might persist for millions of years, tumbling through the Milky Way as a silent ambassador of Earth. Voyager's legacy endures. It taught us about the dynamics of planetary magnetospheres, ring systems, icy moons, and interstellar space. It gave humanity its first taste of cosmic drift beyond the sun's protective veil, and it inspired generations to look skyward and wonder, what lies beyond? Thank you for joining me on this interstellar voyage. If you have questions about Voyager's instruments, the golden record, or life beyond the heliosphere, drop them in the comments. And if you crave more epic tales of spacecraft, robots, and bold explorers pushing the limits of our knowledge, like, subscribe, and share. Together, we'll keep reaching for the stars.